Hello, my name is Gavin Cooper, and this is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. So I'm just going to give you an extreme overview of how the sampler works, but basically it's a method for hierarchically estimating model parameters, a covariance matrix, and random effects for all your participants in a nice efficient way. So the general process is a particle metropolis within Gibbs sampler. So there's a Gibbs step that gets new estimates for our model parameters and covariance matrix. And then for each iteration of the sampler, it uses the current estimate of the model parameters, shown here just as a simplified bivariate normal, to generate a bunch of particles. So each particle is just drawn from this bivariate distribution. But we also generate a bunch of particles from a bivariate distribution centered around the previous iteration's random effects, shown here in the wireframe. And we generate a bunch of particles from there as well. Now, each of these particles is assessed using the log likelihood function provided by the user to generate a new estimate for the random effects. Okay, the best way to illustrate the workings of the package is to work through an example. So here we've got to load the library, and we're going to load in some lexical decision data from Wagamacker's 2008 paper. And we're also just going to reshape that data to work with our log likelihood function. Now, one of the key components that the user has to provide is that log likelihood function. It's a function that takes in a list of parameter values and the data for a participant, and then outputs the summed log likelihood of that data given the current parameter values. So here we've got a high frequency word and the subject responded word. Using the p-norm function, we're calculating the log likelihood for that particular row of the data. Do that for all the rows of the data, sum them up and return it. Some other things that we have to specify are things like the names of the parameters. And finally, if we wanted to, we could also specify a prior. Now that we've got all those key components, we can create our sampler object. This is just a call to PMWGS, providing the data, the parameters, the log likelihood function, and if we had it, the prior. Now that we've created the object, we now need to initialize it. This just creates the very first values for the random effects. Okay, now our sampler has been initialized, we can move on to our estimation. So there's 3 stages of estimation. First is going to be burn-in, so let's start that running. And you can see here that we've got a nice display of the current acceptance rate. Okay, now that burn-in's complete, we can have a bit of a quick look at how the sampling is going. If I just plot those samples, you can see they very quickly move from their initial values through to a relatively stable space. So now we want to run some adaptation. I'm going to start it running now. Okay. So it has now been able to successfully adapt after 48 iterations, so it stopped early. So 48 out of our 200 iterations to create this conditional distribution that we can use for a more efficient sampling procedure in our final stage. Let's start the final stage running now. Okay, now that our sampling stage is finished, we can just have a quick look at one set of participants data. So this is the random effects for an individual participant. So we've got our burn-in phase on the left here, adaptation in the middle, and then the final sampling phase at the end. And just to finish up, I'll point you towards our book down project, which goes into a lot more detail about how the sampler works and provide some worked examples on how to use it in your own data.